Hey there, and welcome to this tutorial. Today, we're going to explore the steps used for processing volumetric data from limited camera capture systems like DepthKit. Using HoloEdit, we'll clean up some mesh defects, compress the volumetric data, and export the final product for streaming. You can follow along using the tutorial's example workspace linked in the video description. Provided in the workspace is a folder named DepthKit example data containing mesh and texture data. This is data exported from the DepthKit system using Studio Mesh Sequence Export, which has already been converted to PLYs and PNGs. Also included are 3 already processed compositions of the various stages. The first one being Mesh Cleaning, containing the completed processing for the test frame range of the Remesh and Clean Mesh stage. The second, Mesh Compression, containing the completed processing for the test frame range of Stabilize Mesh, Generate UV, and Texture Transfer. The third, Completed Processing, containing the completed processing for all stages and intervals. These compositions can be referenced to reduce the amount of processing time needed while following along with this tutorial. Capture systems that use a small number of cameras, like DepthKit, will require a different workflow than data provided by commercial capture stages. HoloEdit includes tools to facilitate this workflow and help improve your capture's overall quality, although it's important to be aware that the final result is still largely determined by the quality of the initial capture. Please ensure that you have the correct settings for your data when generating your PLY and PNGs using the Studio Mesh Sequence Export. If using another software, please refer to that software's documentation to learn more about their tools and settings. Alright, let's get started. We'll start by creating a new workspace with the mesh and texture streams that have been output from DepthKit's capture system. When working in a new workspace or with new data, drag the data into the project window to add it to our workspace. Once the data has been indexed by HoloEdit, select the Make Clip button. The default import settings should work in most cases. If you're using the included example workspace, the data has already been made into a clip as it's being used in the example compositions, so this step can be skipped if you're following along using that workspace. With the data imported as a clip, click and drag the clip title from the project window and drop it into the composition panel. If you're seeing significant issues with the mesh upon loading into HoloEdit, we would recommend returning to the capture system export to regenerate your mesh and texture streams after recalibrating the export settings. At this point, it's a good idea to save your composition here. We would also recommend creating a save file after each stage of finished processing. Let's call this one load_asset_demo. Processing stage requirements and parameters will vary depending on the quality of your clip and the level of cleanup you're hoping to achieve. The clip used in this tutorial does not have many mesh or texture issues and should be the level of quality you're trying to get out of your capture system. With the quality of our data verified, let's begin to process the clip. We'll start by adding a remesh stage to the composition. Remesh uses a voxel algorithm to generate completely new meshes per frame. The depth level determines the size of the grid that the voxels are created on and the level of detail that's preserved from the original capture. A higher depth will better preserve the original details of the capture, but will do less to help clean up the noise, small floating mesh, and tunnels in the mesh. A low depth value can be used to clean up significant mesh issues, but you may lose some desired details along with those you're trying to clean up, so it's important to consider the needs of your project when making decisions early in the mesh cleaning process. For our sample data, the parameters for remesh can be left at default. Next, we'll add a clean mesh stage. The parameter requirements of this stage will depend on the quality of the clip. In most cases, you want to have the following parameters. For enabled decimation, we want to make sure this is enabled. This will help reduce the triangle count of the mesh to decrease processing time and achieve a more performant playback. For fixed degenerate triangles, let's make sure this is also enabled. Fixed degenerate triangles is one of the core functions of the clean mesh stage and will help prevent errors in processing caused by zero area and malformed triangles. For decimation target tries, this should be set to a reasonable value. Our recommendation is between 30,000 and 60,000 depending on the complexity of your clip. For this clip, we'll set the value to 35,000. For remove small components, we want to make sure this is also enabled. This will add a final level of cleanup for any floating mesh noise left around the remesh stage. The minimum component area will determine the area of removed components. 0.1 meters is the default threshold and can be adjusted as needed. Now, we won't need to bride or remove all but largest components for this particular clip, but for future reference. Debride should be enabled if you have a lot of jagged edges and strips of geometry around your mesh. Remesh should have already removed such defects, but if you're skipping the remesh stage, it may be necessary to enable this parameter. For remove all but largest components, this is used if your capture has a lot of unwanted floating mesh around your actors. Next, we'll create intervals in these stages. Now, as you're processing, it's rare that one set of parameters will work for the entire clip, and it may take a few tries to figure out exactly what parameters are going to create the best results. With this in mind, we recommend selecting a small range of test frames over different points in your clip to begin figuring out what parameters are going to work best. By breaking your clip up into small test sections, you'll save a significant amount of processing time while trying out different parameters, as opposed to trying to process the entire clip each time. Once your test ranges are returning desirable results, you can then apply these parameters to the remaining parts of your clip. Alright, so to get started, click and drag to select your frame range, frame 9 to 22, over the two stages. Right-click the selection and choose Add Interval from the right-click menu. Select both intervals, right-click, and select Execute. Depending on the density of the mesh and the length of the interval, it may take a bit of time to upload the job. Once the results have returned and you're satisfied with them, we're ready to prepare the clip for compression by applying stabilization to the data. Start by adding a stabilized mesh stage. There are two main parameters to be aware of while you're processing your clip. The two most likely to affect your stabilization results are segment max error and sample radius factor. For segment max error, this determines how much error is acceptable between the source mesh and the result mesh of stabilization. If the value is exceeded, it creates a break between segments and begins deformation with a different keyframe. If you're finding consistently bad results from the stabilized mesh stage, you can decrease this value. But keep in mind that smaller segments reduce compression. Start with the default value. Then, if you find you are seeing long segments with bad deformation, try decreasing it. Start with 0.05 and decrease further as necessary. For sample radius factor, having a higher value here will speed up processing and catch larger movements consistently. If there are a lot of important surface details in your capture, you may want to keep the parameters set to the default values. So these are the go-to parameters when working within stabilized mesh, and we suggest that you start here. However, depending on your capture, you may have to make additional adjustments to other settings. For an in-depth exploration of stabilization, please check out our Advanced Compression playlist and Stabilized Mesh documentation linked in the video description. For this clip, we will leave the ArrowMex as is and set the sample radius to 14. We'll also enable Use Hierarchy Node Sampler and Use Double Precision for faster processing and better results. Next, we'll need to generate UVs for the clip because the remesh stage removes existing UVs when the new meshes are created. Generate UVs can be used at any point following the remesh but before the texture transfer stage. We'll use it following the stabilized mesh stage because it will only need to generate one new UV per stabilized segment, so the required processing will be reduced on the stabilized clip. We'll leave the default parameters for this stage. Next, let's add a texture transfer stage. With texture transfer stage selected, drag your load asset containing the texture stream to texture source stage and ensure that texture transfer method is set to closest point. The closest point method allows for more surface variation between the original input mesh and the mesh following stabilization, making it easier to get a good looking product with less time spent making sure the surfaces of the stabilized mesh matches the source mesh exactly. As a test, we'll select frames 9 to 22 on the three new stages in the timeline and create an interval for the selection. Select the intervals and execute them. Alright, let's jump ahead and check out our results. Everything's looking good. The final step to compression is applying Ssdr. We'll add an Ssdr stage and create an interval for the whole clip. For a simple clip like this, the default parameters will work. We'll also create intervals for the remaining frames for the stages remesh through to texture transfer. Select those intervals as well as the Ssdr interval and execute the stages. Alright, so our clip is in process and we're ready to share our volumetric video. Start by selecting Export Composition from the File menu. We'll upload this clip for streaming so we don't need to set the output path location. We're going to upload the whole clip so we can leave the default output frame range populated. Then, select the plus button to create a new export sequence. In the Output Sequence Type dropdown, select Streaming. We'll use the default settings to create a full adaptive streaming profile. Review and accept the transcode costs and balances and agree to be billed by enabling the checkbox beside Accept. Select Save, then select Export. It will take a bit of time for the upload and packaging process. Once upload and processing are complete, a window will open to display two pieces of information. The GUID, which identifies the clip, is used to reference the clip being played by the HoloStream player and acts to reference the clip in storage. The URL will allow us to preview the clip as well as share and embed the content as required by our project. The URL can be provided to an OMS player, such as a Unity OMS plugin, to play media directly from the HoloStream servers, or open in a web browser to preview your streaming clip. Now that our upload is complete, we'll click on the preview button to check out our streaming content. Thanks for watching this tutorial on limited camera capture systems. For more information about working with HoloSuite, please check out some of our other tutorials on our channel, or the technical documentation linked in the description below.